Good morning, guys. I'm really disappointed with the attendance. I mean, I don't know what's happening to you guys. Is there like a midterm? Is there like a midterm test today or no? Huh? Oh, okay. Okay. Anyway, the couple of announcements. The quiz number 5 is this one. It's due 11 a.m. today, so if you haven't done it, please do it by 11. I will send an email later today, just inform you what the correct answer is and how the correct answer was obtained and what mark you got. Okay? And number 2 is the tutorials. There are 6 videos for the tutorials this week. So if you haven't been to any of the tutorials this week, please watch these. And there's also this video here which gives the this video gives the video. This is the solution for all the questions in the tutorial sheet, this video, right? So please watch all these videos if you haven't been to the tutorials, okay? Right, this week is only one video I asked you guys to watch, namely this one. I hope you did. I hope you watched this video, guys, right? There's only one video. Yeah. So this video is about maximum likelihood estimation, right? So last 2 weeks, just to recap, last 2 weeks we talked about point estimation, right? So in other words, if you got a population parameter, how do you estimate it? Normally the population is so huge, you can't access every single person in the population. So what we do is we draw a sample, say 100 people, and based on the sample, we estimate the population parameter, right? And we call that theta hat. And there are many ways of estimating parameters. There's not just one theta hat. There could be like 10 different estimators for theta hat, right? And in that case, how do you determine the best estimator? Like I introduced 2 criteria, namely the bias and the MSE, or the mean squared error. Now, if the bias is 0, then it's a good estimator. And also, if the MSE approaches 0 as the sample size approaches infinity, that's also a sign of a good estimator, right? Now, what we did not talk about in the last 2 weeks is how do we construct estimators in the first place? Right. There are many ways of constructing estimators, right? And one popular method is known as maximum likelihood estimation, right? So that's what I'm going to talk about. I'll just go through the notes quickly because I assume that you have already watched the videos, right? So how do we construct estimators, right? That's the question. And a popular method is the maximum likelihood estimation. Now suppose, okay, this describes the method of maximum likelihood when you have continuous data. So suppose you have data from a continuous distribution with the density given by this, and the parameter is theta. Then the maximum likelihood procedure, or the procedure for obtaining maximum likelihood estimators has 4 steps, right? The first step is to write down this, which is known as the likelihood function. So it's the product of the density function at xi. Xi is the ith data point, I from 1 to n, right? And the second step is to take the log of the likelihood. So it's the log of this, which is equal to this. Remember, I don't know whether the log of a product is the same as the sum of the logs. So the log of this is equal to the sum of the logs, right? And the third step is to solve this equation, that is the derivative of log of L with respect to theta, set it equal to 0, and solve this equation for theta. So I'm calling this star. And the fourth step is to make sure that the solution of this equation corresponds to maximum. And how do you do that? I'm sure you did this in calculus, is to take the second order derivative, and if the second order derivative at theta equal to theta hat is negative, then the solution corresponds to a maximum, right? So we can say theta hat is a maximum likelihood estimator, right? So this is the procedure when you have continuous data, or data from a continuous distribution, right? The procedure for discrete data, like if you have data from a discrete distribution, the only difference is that in place of using the F, which denotes the PDF, you use P, which denotes the PMF, or the probability mass function, right? So the first step is just the product of the probability mass function at xi, I from 1 to n is the sample size. And we call this the likelihood function of theta. The second step is to take the log of the likelihood, which is the sum of the logs. And the third step is to take the derivative of the log with respect to theta and set it equal to 0 and solve this equation for theta. Let me call this star once again. Now, to make sure that the solution of this equation corresponds to maximum, you take the second order derivative and compute that at theta hat. And if that is negative, then the solution of this equation star corresponds to the maximum of the likelihood function, and hence it is a maximum likelihood estimator, right? All right, so this is the procedure for discrete data and the procedure for continuous data in the previous page, okay? Now, there are some properties. I don't expect you to know the proofs of these properties, but it's useful to know these properties. The first property is that the maximum likelihood estimator is always asymptotically unbiased. Remember, asymptotically unbiased means that the limit of the bias of the estimator approaches 0 as n approaches infinity, right? The second property is that a maximum likelihood estimator is always consistent, which means that the limit of the MSC of the estimator is 0 as n approaches infinity, right? The third property is known as asymptotic normality, which means that if you take the limit of this, that is root of n times theta hat, which is the maximum likelihood estimator, minus the true value of theta, right? Then this approaches the standard normal distribution. Well, sorry, not necessarily standard normal. It approaches a normal random variable as n approaches infinity, right? So this property is known as the asymptotic normality property of a maximum likelihood estimator. And the final property is known as the invariance property, which says that if you have a function 1-to-1, g, I hope you know what 1-to-1 is, right? That is, a 1-to-1 function is a function for which for every x there's only one y. I'm sure you did this in analysis, or I'm sure you did this, right? Or no? A 1-to-1 function is that for every x there's only one y, one corresponding y, okay? So if g is a 1-to-1 function, then g of theta hat is the MLE for g of theta, right? And this is known as the invariance property. All right, so these are the 4 properties I would like you to know. And there's no need for you to know the proofs of these properties, only be able to apply them for problems, right? I will do some problems in a minute. Okay, right. Any questions so far? on the video. Any questions on the video, guys, so far? So let me start doing some examples, as always. So I will do some examples on the maximum likelihood estimator. Example 1. All right, guys, so this is example 1. You have a random sample from this distribution where A is the parameter, and we want to find the MLE of the parameter A, right? Now, clearly, this is a continuous distribution, right? I'm sure this is actually the exponential. I'm sure you've seen this before. This is known as the exponential distribution, right, which is a continuous distribution. So the first step is to write down the likelihood function. The likelihood function is a function of the parameter A, right? So if you look at, let me show you. So in this case, the likelihood function is the product of the density function for I from 1 to n, right? So this is going to be the product I from 1 to n of 1 over A times E minus xi divided by A. So you see I'm using the first step. There are four steps to finding an MLE, right? I'm in step number 1, okay? Okay. Now if you simplify this, guys, you should simplify this. This is where your math comes in. This is what you will get. You have to be very careful in simplification. I mean, I've taught this course quite a few times now, quite a few years now. I mean, a lot of people have problems simplifying products. This is something I cannot teach you. I mean, this is something you ought to know from your other courses you have taken, right? Many people have problems going from this line to this line. I do not understand why, because this is something you ought to have learned a long time ago. But if you want some help, I can give you some help if you like. If you need help with simplifying products, there's a video about it. You should listen to this video.
When I was a student,
Sorry. Listen to this video. It gives you some help on how to simplify products of functions. Like, for example, the product of a constant is constant to the power n, right? The product of constant times xi is constant to the power n times the product of xi. The product of exponential of a constant times xi is equal to this. And finally, the log of a product is equal to the sum of the logs. So these are, you may find, I mean, these are some basic stuff. I'm sure most of you know this, but in my past experience, many had problems simplifying products. So if you forgot these facts, just please try to remember these facts, right, about simplifying products of terms, right? So let me go back to where I was now. This is big 6. Yeah, okay, here we are. Okay, so this is what you will get if you simplify this product here, right? So part 2 is to take the log of the product. So it's log of this guy here. So if you take the log of this, you get minus right? This is the log of the likelihood. And part 3 is to differentiate the log likelihood with respect to theta, which in this case is A. So if you differentiate the log likelihood with respect to A, you get minus n over A, and the derivative of this gives you plus 1 over A squared times sum of log of xi. Okay, guys, and now I'm going to set this to 0. Okay. Now, if you solve this equation for A, this is what you will get. You will get A hat. I mean, the solution I denote by a hat. So whatever the parameter, you put a hat on top. Okay? Okay, so the A hat is the solution of this equation, and it's equal to 1 over n and this is the sample mean. All right? Now, the last step, step number 4, is to make sure that this solution corresponds to a maximum of the likelihood. To do that, you need to take the second order derivative, so which is the first order derivative of this one. So it's going to be n divided by a squared minus 2 divided by a cubed now we need to show that this guy here is a negative number. So how do we do it? I mean, there are many ways you can do this. How can we show that this is a negative number? One way to do this is as follows. I'm going to pull out 1 over a cubed outside. So this becomes, in brackets, n times a minus 2 times okay. And in the next step, I'm going to replace a by a hat. Remember, a hat is this guy here, right? So I'm going to replace a by a hat. So this will become now we know that a hat from here, we know that a hat is equal to 1 over n times the sum of xi. So n times a hat, if you multiply this by n, you get okay? You follow me? You see what I have done? I have replaced a hat by this expression here, right? So n a hat becomes this. Now what you have here is the sum of xi minus 2 times the same term, right? So hence, this must be negative, right? So hence, Are you with me, guys, or no? Yeah, so this is how, I mean, sometimes the last part can be tricky to show, but you have to use all the math you know to show that the second order derivative is negative. Okay? Any questions, guys, please? So that's question number 1. Question number 2, this easy one. Sorry, example 1. This is example 2. So once again, what you have here is a continuous PDF, right? Remember, PDF automatically means that it has to be a continuous distribution, because PDF only applies for continuous, whereas PMF is for discrete. Right? So you should be able to tell immediately from this, right? Okay, the first step is to write down the likelihood function, which is the product of the density function, right? So now you should take the product of this. Once again, let me do this a bit slowly, because you might have found, I mean, I don't need to do this so slowly, but I'm doing this slowly because just for the benefit of you, right? The product of A is a constant, right? So the product of A is A to the power n. Now then you have the product of this term here, which is A to the power n times the product of xi like this, yeah? So this, I mean, especially the first part, you have to be very careful, because if you get the first part wrong, then you don't get any credit for the rest of the question, right? Okay, so you have to be careful with the first part. Then you take the log of the likelihood, so which is log of this guy here, which is n times log A, plus the log of this term, which is A minus 1, times the log of this product of xi. Right, which is n times log of A plus A minus 1. Now, log of, I just mentioned to you a few minutes ago, one of the properties I showed you, let me show it again if you want. One of the properties I showed you is that the log of a product is equal to the sum of the logs. So you can write this as the sum of the log of xi. Okay? The third step is to take the derivative with respect to A. So this is n divided by 8 plus yeah, this is the third step. And the fourth, before we need to solve this equation for a, which is easy. So you get a hat. Remember, just always put a hat on top of the parameter when you get the solution, right? So hat means it's an estimator, right? So a hat means it's an estimator of a, right? Okay, so this is minus n okay. Right, now to make sure that this is an MLE, right, or the maximum likelihood estimator, we need to show that the second order derivative which is the derivative of this, which is minus n over a squared. And this is clearly negative. I mean, this is easy here because clearly minus n over a squared has to be a negative number, right? So the conclusion is that a hat all right? Sorry. Any questions on this, guys? Are you okay with this? Are you okay with this, guys? Sure. Yeah? Okay. Right, now let's do a discrete example. So the two examples I've looked at so far are both for continuous data, right? Now let's look at an example where the data are not continuous or discrete in this case. So suppose okay, so let's look at this. Now, for discrete data, you need to follow this procedure here, right? So, now, there are remember, for binomial, you have two parameters, m and p. Now, here I'm assuming that m is known, so the only parameter that is not known is p. And we want to find the MLE of p, right? Right. So let's first step is the likelihood function of p, which is the product I from 1 to n. I'm sure you remember the probability mass function of a binomial. What's that? Is m choose xi to the power p choose x to the power I, 1 minus p choose m minus xi. I mean, if you don't remember this, just there is a link here. I'll show you the link. If you go to the top of the page, you see there's this link here. You can click on it, and it will tell you so this is the probability mass function. This is the probability mass function of the binomial. right? Now, this is, I mean, I can tell you, this is an example I gave as a quiz last year, not this year, last year, and many had problems doing this example. This was one of the quizzes last year. Now, especially with the simplification. Okay, let me do this slowly, okay, so that you know what I'm doing. Now, let me, there are three terms here, right? So the product applies to all these three terms, right? So, so the first, this is the first term, right? The second term is this, right? And the third term is this, yeah? And this one, you can't really simplify a lot, right? So you have to leave it like this. Don't be alarmed by the, I mean, it's not, so you have to leave the, now this one, what's the, what does it simplify to, you think? This will be P plus the sum of xi, I from 1 to n. Yeah? And this one, 1 minus P times the sum of mxi, so sum of m minus xi, I from 1 to n. Hope you can read my writing. Yeah, so you get this as I mean, this is not really, this is really mathematical skills. You should think you have forgotten this stuff. Please try to brush up your math, right? So this becomes right. Now you have here sum of m minus xi. Now if you take the sum inside, you will get the first term will become m times n, because m is a constant with respect to I. The second term will become the sum of xi. Yeah, you follow me? So this is the likelihood function, right? The second step is to take the log of the likelihood. So I'm going to do this in one step, although I can do it slowly, but I hope you don't mind if I do it in one step. So you should do it this is the log of the first term. The log of the second term is this, and the log of the third term is this, okay? All right? You okay so far? Yeah? All right, the third step is to take the derivative. Some of you look perplexed, I don't know. Are you guys okay so far or what? The third step is to take the derivative with respect to p, right? There's no p in this, right? So the derivative of the first term is 0, right? There is a p in it, which is log of p. So the derivative of log of p is 1 over p. So it's going to be is going to be this. And the derivative of the third term, so you've got to differentiate the log of 1 minus p, which is minus of okay? Are you with me? Right, so this is the derivative that you will get when you differentiate this with respect to p. Now, if you set this to 0 and solve for p, once again, I'm going to do this in one line, but I mean, I'm sure you guys know how to solve equations, right? I hope I don't need to show you. So you should solve this equation, right? For p, you get 1 divided by m times n divided times the sum of xi. So this is what you will get. So that's only up to step number 3. Now step number 4 is to take the second order derivative, which is so you should take the derivative of that is going to be minus and the derivative of this is going to be minus is going to, so it's going to be, there are 3 minuses you get, minus, 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 so you get, eventually you get minus. All right, so this is the second order derivative with respect to p, and clearly because of the minus and the minus, this is negative, right? Right. So the answer is that hence all right. So these examples looks a little bit complicated, but it's not real. It's just the math. I mean, it's just the math part. You know, some of you will find it difficult, but if you have problems, especially with the math for the first part, it's really. I mean, this math here. I mean, I know some of you may find it difficult. So if you do, just please try to brush up your math, okay, on how I got from this line to this line here, right? Okay? You guys okay or what? Any questions? Because every year I taught this course, I find the same problem, like I find people making the same mistakes every year, so I'm sure you can do, guys, better, right? Okay. Any questions on this, guys? You okay? All right. Okay. I will scan this. I will scan everything I write down and put it on the course website after the class. So don't worry if you miss some details. It's okay, right? Okay, now the next example is a related example. Example number 4. Now, in this example, I'm going to suppose x is a binomial variable with parameters m and p. Okay? Once again, assume m is known, but p is not known. right? Now, do you see what the difference? Okay, let me put this together, right? Do you see the difference between these two examples? In example number 3, we had n data points, which are IID, each coming from a binomial with parameters m and p. But in the example 4, we have a single data point, x, which comes from a binomial with parameters m and p. So these two are not the same questions, and the answers will be different. You will see in a minute why. Okay? They are not the same, right? Okay, so now the first part, because we have only one data point, the likelihood for P is going to be the product. Okay, let me show you okay, just a minute. Let me show you the procedure. This is the procedure. Remember, first step is to write down the likelihood function, which is the product of the PMF from I from 1 to n, where n is the sample size. Now, in this example, the sample size is 1, because you only have one data point. Okay? Okay, so this would be from I from 1 to 1 of the PMF of the binomial, which is what? M choose x to the power p to the power x, 1 minus p to the power m minus x. Do you follow? Compare these two. Like, let me show you what I'm talking about here. Excuse me. In this example, in example 3, right, you had n data points. So the product was from 1 to n of the probability mass function for binomial. But in this example number 4, this is example 3. In example 4, you only have one data point. So the product is from I equal to 1 of the PMF, which is what I have written down here, right? You follow that? Because it's something easy to get confused, right? Which you have. So in this case, this will be just simply m choose x, p to the power x, 1 minus p to the power m minus x. Okay? So that's the first step. The second step is to take the log of the likelihood, which is the log of this, yeah? And the third step is to differentiate with respect to p. So you get x divided by p minus m minus x divided by 1 minus p. And you set this to 0 and solve for p. You get p hat equal to, if you do the math, you get p hat equal to x divided by n, right? Now, step number 4 is to take the second order derivative, which is the derivative of this guy here, right? So it's going to be right? And this is clearly negative because of the minus, right? So hence, this so you see here that this is the MLE when you have one data point, and compare with in example, let me write down, in example 3, the MLE was This was the MLE in example 3, right? Because we had, in example 3, we had n data points, not just one. So if you put n equal to 1, if you put n equal to 1 into this formula, this will reduce to this, as it should, right? The n equal to 1 gives you this formula back, right? Okay. Are you guys okay with this or no? Come on. Talk to me, guys. Are you okay? All right. Now, one last example I will do if I have time, or maybe I will ask you to do. This is something tricky, really. Do you know the log normal distribution? Or you heard about the log normal? So this is example . If you don't know what log normal is, let me show you. You should just go back to the top of the page, click on this link. You will see, is it here? Oh, yeah. This one here, this is the log normal distribution, right? If you haven't seen this before, it has this as the PDF. So it's 1 over x times square root of 2 pi times sigma times exponential of this guy here, right? The notation ln stands for log normal, right? So it's with parameters 0 and theta squared, right? I don't think I'll be able to finish this today, right now, but I will just write down the first line. The first line is the likelihood function, which is going to be the product I from 1 to n. So if you use the formula here, you will get 1 over xi times the square root of 2 pi times theta, then exponential minus log of xi mu is 0 divided by theta squared divided by 2, right? This is the formula for the PDF. It's a continuous distribution, log normal, right? Now, if you simplify this, guys, this will be 2 pi to the power n over 2 times the product. I'm doing this quickly just to save time. Hope you don't mind. Times this, and then exponential of minus 1 over 2 theta squared times I from 1 to n of log of xi squared. So this is the simplified form of the likelihood function, right? And then you take the log, let me also write it down. The log likelihood is going to be minus n over 2 times log of 2 pi minus the sum of log of xi minus 1 over 2 theta squared. Oh, there's a theta I left out here. Sorry, guys. There should be a theta to the power n here, which I left out. I hope you noticed that. Right. So this is the log likelihood. I will leave the remaining 2 steps for you to do. Now, if you have trouble doing them, please feel free to contact me 24/7. All right, so this is step 1, this is step 2. So try to please complete the step 3 and step 4 by yourself. And please contact me if you have trouble, right? Okay, guys, so have a good day and have a great weekend. And I will send you the solutions to quiz quiz 5 later today, okay? Yes.
Can I ask you a few questions of some steps that you did?
Yeah, sure.
This was the main one. Sorry. Did that differentiate to 0 because it's that just a constant?
Yeah, because there's no p in it. You see, p is the parameter.
Yeah.
It doesn't involve p, so the derivative is 0.
Yeah. I don't know how you rearranged that to get p.
Well, there are a few steps I left out. Yeah, I mean, you should do the math. I'm sure you know the math, right? You should do the math for it. This is what you
Well, I
will
tried
get.
to do it and I couldn't do it.
You couldn't? Maybe there's can you come to my office later today?
Yeah, okay.
You know my office. Sorry, 2.223. Maybe there's a class here today. I don't know. I can do it now. You should.
Or you can just tell me the quick steps of what you would do and I'll do it on my own.
Oh, let me get some paper.
Just the basic outline.
Yeah. I know. But let me, if I have, I don't know whether there's a class today, but right, it's like this, ma'am. So you have sum of xi divided by p equal to mn minus the sum of xi divided by 1 minus p.
Yeah.
Now what you do is you take this to the left-hand side, you take to the right-hand side, so you get 1 minus p times the sum of xi times p times this guy here.
Yeah.
Yeah?
Yeah, thanks.
And then you can write this here as sum of xi minus p times sum of xi,
Yeah, I did this.
and this the same thing, right?
Yeah.
Then take this to the right hand side. You get sum of xi equal to p times mn minus sum of xi plus sum of xi. You get it? If you take this, so these two cancel.
Right, oh yeah.
So p hat is equal to sum of xi divided by mn. That's what I have. I know quite a few steps, but because of the time, you can keep this one.
Thank you. There were 1, 2 things.
Sorry. I think we need
Just that step as well.
Yeah, that's basic math, ma'am. It's just you can write this as this. That's allowed. That's basic math.
Thank you.
Yeah, sorry.
That's all right.
Just carry on. Question.
Yeah.
Are we supposed to memorize all the PDFs of all the distributions, or will we be given a formula sheet?
You will be given a well. In the website I showed you, there is a formula sheet.
Yeah, but are we supposed to memorize all of them?
No. It's only 1 page long. If you look at the website.
Will we get